Hello everyone, it's June 20th. It's a Sunday. Alright, let's get ready for it. It's more likely going to be a difficult question as well, but we are prepared. Alright, see if anything worth, nothing here. Alright, take a look. Swimming in rising water. Okay. On a n by n grid, each square represents the elevation at that point. Now rain starts to fall. Time t, the depth of the water everywhere is t. You can swim from a square to another four directionally adjacent square if and only if the elevation of both squares individually are at most t. Okay, at time t, the depth of the water everywhere is t. You can swim from a square to another if and only if the elevation of both squares individually are at most t. Yeah, if it's smaller than t, you can swim there. If it's larger than t, then you got blocked. You can swim infinite distance in 0 time. Of course, you must stay within the boundaries of the grid. You start at the top left corner. What is the least time until you can reach the bottom right corner? Ooh, okay. All right, what do we have now? We have a grid with 0, 2, 1, 3. So the starting position is 0. So at time 0, you're at 0, 0. Yes, you cannot go anywhere because four directionally adjacent neighbors have a higher elevation. So at time 0, you cannot go. At time 1, so the water level is 1, right? So you can go to the place with height at most is t. So at time 1, you can reach so that's time 0. At time 1, you can reach. Oh, at time 1 you can reach this 1, 0, right? 1, 0 position. And then at time 2, hold on. I can go multiple places, right? It doesn't say that each time you can only move 1. It says you can swim infinite distance in 0 time. So can I like zigzag? Can we zigzag to different places? Huh. Let's see. So yeah, so from time 0 we stuck at 0. Time 1 we can go to here, right? And time 2 we can go back. But why do we go back? And at time 3 we can come here. So it has to be 3. And when the depth is 3, we can swim anywhere inside the grid. That is true. Okay, take a look at this. The final route is marked. We need to wait until time 16. So that is 0, 0, and 1, 2, 3, 4. 0, 1, 2, 4 are connected. Yeah, so we find this path, 16. Yeah, so we wait for 16, we can just whoosh, go. So that means the question is to find, I mean, if we wait for 24, it's definitely going to working, right? And we just need to find a path that contains, so we need to find a path that is four directionally connected with the maximum value in this path being the minimum, all right? Okay. What's n? N by n, so at least 2 by 2. Okay. The minimum maximum value in a path. I mean, there are lots of paths that can go to the end. And we want to find the minimum path. It doesn't matter how long the path is. We just want all the things, right? All the cells in this path to be as small as possible. It can even go, go in circles. It doesn't really matter because we can swim in infinite speed, right? We can reach any place in 0 time. Okay, so usually I think we can go backwards. Like say we have 6, right? So which means we have to wait at least 6. And then from here, we see there are 2 paths out, right? And we have a 20, we have a 7, so okay. We can wait until 7, so we go here. So every time we go here, right? And then we go here. And from this position, we can only go up. That's only 2 ways we can go. We'll go up, up, up. Up here, we can go this way or this way. So we go this way or this way. We'll go this way. So every time we pick the small, and here we go here. So in this path, the largest we encounter is 16. And it's 50. The maximum is 50 by 50. Okay, let's think. And the minimum is going to be 6, right? How do we search for it? Greedy. If we do greedy, we're always trying to find the path with the smallest to go. Now that I can already see problem. All right, we can just set it up very smart. Right, we can say we lead up to here, and then we just set it very smart for this one to be a larger value. Right, we can have something to be a larger value at a spot that would go there instead of going because this is a greedy path, right? This is a greedy path. If every step we choose the smallest, it could be like if we choose the smaller, every step we choose the smaller of the 2. Of the 4, if you think about it, right? Every step we choose the smaller of everything, and then it could be just a local minimum, and then we have a true. But hold on, every step we choose a local minimum, right? That means we are avoiding going. So the problem is if we go the local minimum, and eventually we will hit a position where the local minimum is huge. But we can avoid that. Like the local minimum is big, but if we go the other way, right, then we hit something that is. So let's say if this one is like a slightly bigger, right, and then we keep going. And say both of these are huge, right? Let's say both of these are huge. Then we just take this as a huge value. If this value is smaller, this value is much bigger than this, then we take this one will be better. Yeah, it is possible that if you do greedy, it's not going to work. So that's not, at least not from the start. How about from the end? From the end, shouldn't that be the same, right? If we go from the end, we say if we always want to pick something with small, we can have the exact same issue. Remember, it's not the shortest path. It is the path with the smallest number on the path. Hmm. Hmm. Have to make at least 6 to reach here. Can we like expand? I don't think it works that way. I'm thinking about if it's possible to think like a DP, like if we have a solution for a smaller grid, right? If we have a solution for a smaller grid, what will happen if we increase the grid? That doesn't make sense. That doesn't make sense. If we have the smallest to reach every single position, right? If we have the smallest to reach every single position, then we know the smallest to reach every single position in the bigger one. Hold on. So we know has 0, right? Then first level is this, so we know the smallest to reach each one is this, right? And then we add another layer on top, 2, 22, 13, 13, and 12. And then, let's say we know to reach 24, we need 24, so we need 12. To reach 12, what we can do is we can reach 12 from 24, or we can reach 12 from 13. So it's from 24, we're going to take 24. Just 13, we don't know, right? So if we want to reach 13, it's going to be from 23 or from 12. Then we are stuck in an infinite circle, right? Infinite circle. When we say we can reach 2, only has one way to reach, or we can reach from 22. I'm really bad at this type of problem. I think I got stuck in this type of problem last time with a slightly different question. When it's like it can go all directions. I was struggling from it. It can go all directions. Go all directions means what? How about like at each time point, we figure out what are the positions that's reachable. Right? At time 0, it's this one. At time 1 is here. Time 2, 3, 4, 5 is here. But 6 is going to be this. Right? These are visible. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And boom, we have a path. But how do we know we have a path? I mean, it's 50, right? So 50 by 50, we can do 50 times 50, 2,500. 2,500, we can screen 2,500 a couple of times. All right, we can do that a couple of times. Each time we scan it, and every time we scan, we try to see if the available cells can be connected to form a path. How do we see that? How do we tell? How do we tell if the things connected can form a path? do you mean by form a path? Form a path means we can connect it to each other, right? 3 can connect to each other, 4 can connect. When I am visible, right? Every cell, like when I am visible, then I can look to my neighbors to see if my neighbors are visible. If my neighbors, none of them are visible, then I am by myself. If some of them are visible, then I can form a connection. And the thing is, how do I tell that this connection can be used? Are you saying that at each time, after each round, we have to go from 0 to run a path to the end? Like a DFS? That's possible. So every time point, right? Each time point we run a DFS. Each time point we run a DFS. Try to see if we can find the end. Well, the DFS is going to take, it's going to take time, right? Like, because it's not a one direction. The DFS can take 4 directions. I need to figure out how does this 4 directions work. Yeah, I can take 4 directions. You can't just do, I mean, technically you can do DFS. Or like every time you can go, what is the place as far as you can go? I mean, if you set a number that we know which one is reachable, we don't know which one is reachable. That's the problem. We don't know. Like, well, it's 12, right? I don't know when this 12 is reachable. When the time hits 12, well, at 10 to 12, it is reachable, but let's say if we have like 17 here, right? 17 here, then when it's 12, I am not reachable by anybody. Okay, think again. We know that this will be reachable by time 6, right? So we just need to construct a path for the minimum. The minimum will be 6, right? If I can find a path. So we need to find all the reachable points by time slot 6. So we can just say this is reachable. Let's say these are reachable with whichever is reachable from this, and then we have reached. We don't go again. We just go to find all the points, right? All the points that can be reached by time point 6. We can put a list of all those, right? And then at time point 6, all those reached, we can list them out. Like in this case, it can be 0, 1, 2, 3, 4, 5, and 6. Everybody else is not reachable. What does that do? Right? What does that do? Reachable from 0, right? Reachable from 0. And 6 is not reachable, right? Reachable from 0. What that do is we know currently where we can go. So these are the points that we can go, right? And then we say I want to do 7, right? I'm going to do 7 to see if there's any point that is reachable by 7. No points are reachable by 7. We have to go all the way up to 16 to have the first one be reachable, right? And then from 16, we can keep saying, and we go to the end, then we reach the end. So what exactly is the rule? What exactly is the rule? So at each point, we find, at each time, we find which cells are currently reachable from 0, right? And that can be done by like a DFS type of thing, right? So we just keep going, look around, keep going, look around, keep going, and then we record all the points that's currently reachable at this time point. Now go to the next time point, we go through the entire list again and see where we can reach, right? Which point we can reach. I mean, in that case, it's possible if you want to go from each point out, right? Each point, bless you. If you want to go from each point out to see which one we can go, and then if it's a new point, we save it to the next round. Then if it's nothing, then we just keep everybody in a list. And if from a point we have already exhausted all possible points for that thing, then we remove it. So because we're already exhausted. So it's more like a BFS instead of a DFS. All right. So at each time point, we record all the points, all the cells that's currently reachable from 0, and also who still has cells that's unexplored. And we keep updating this list every single time until the end point it can be reached. And that will be the answer. Let me give this idea a shot. It might prove to be working. Oh no, I just typed the wrong thing. I forgot to copy it first. Sorry. Copy this. 20, ST, 20. There we go. Oh, I think we have too big a font. It is huge. Alright. This is good. Okay, I have this idea. Alright. So what we're going to do is for each time point. So we're going to say for t in actually no, t and then equal 0, right? And while true. So at time 0, what are the things that we can see? So all we need is a thing that allow us. So it's going to be a queue, right? So it's going to be a queue, right? And then we're just going to pop everything in the queue and then push new thing in it. So times 0 is going to be 0, and we're going to push in the value, right? The value. And available, right? Available will be, how do we compute the total available? Available will be your ij. Total available, right? Total available. Okay. So it's actually going to be, hold on, let me think how the data structure is going to look like. Well, it's going to be your position. We're going to have ij in it, right? We're going to have ij in it. And we're also going to have ij and the number of possibilities you have. Like if I explore, if I'm here, right? And I explore next one. And then if I can go, I push it in, and then this one will reduce. Okay, so we can just be what, 0, 0, and total possibility. So we have 4. Everybody has 4 to start with, right? So I'm gonna say temp equals this, and while q. Actually, let me say while q. So eventually we will run out. I mean, eventually we'll reach the end. All right, no matter what, we'll reach the end. So we can say that. So we just say for cell. So for I, j, to explore in Q, right? And then we can say if, I mean, Q should be something we need to, hold on. What if the start is larger than 0? Well, then the t is going to be, yeah, we have to start. All right, the t is going to be grid 0, 0. They cannot be smaller than that, right? Then we solve the problem. So I come out and we say if, all right, if, and of course, if we put in a q, then definitely is larger than or equal to, right? So we're coming out, and then we just going to try to see, right? Try to see for the next time point. Next time point. T is this, right? So T is 0 or T is this. We're going to see which ones we can go, right? So we're going to pop out the first one and see its surroundings, right? And I'm going to say if I is equal to 0, I is 0's first row, or I equal to, so we're going to have m and n. So mn equals len grid and len grid 0, right? n minus 1. So we say if we have the first row or the last row, then your 2 that minus equal to 1. But that only happens in the first time. So we'll do this when we go to it. So not doing it right now, which means we have to. This is only two to explore, right? 2 things to explore. That's not when we do it. So we get this test cell out. We know we can go. We need to see where's the next thing that we can go, right? Where's the next thing we can go? So we put in the temp. We have to go. We have to do this until. So we have to explore the entire thing, right? Until. Let me think. Or maybe it'll be easier to do this by DFS, right? Maybe it's easier to do DFS from 0, 0, and we go as far as we can. But for the DFS, the things that we have encountered before, then we have to do it every single time, right? Well, I just want to know the edges that we can reach, right? The absolute edge that we can reach. So we put everybody that we can reach into a new queue, all right? And then for the ones that has been, if it's now I have to put it back in, all right? We have to keep running this until until there's no more we can reach, and that is the end. Then we add one, which means we have to say while q, right? Q equals 10. Then we just remove the, no, it's not while q. It's going to be while another loop here, right? And we say temp is this, right? And then we try the next one. If the next one's good, we put into the temp. And if the current one has more to explore, we put into the temp. And eventually we'll create a temp, which is the most frontier that we can go from the current perspective. And then we do Q equals temp, coming back to this again. And then this one will end if temp is empty, right? So nothing gets pushed into temp. That means the Q is the current furthest that we can go. And then we add T plus 1 and check the Q, okay? So we have IJ, we have to explore, then we need to see what we can do to explore. So we have 4 directions, right? For DI, DJ, in range. So 4 directions is going to be, not for range, it's going to be this, right? We're going to be, let's go systematic. Let's go up. So up is going to be -1 on I and 0 on J, right? So we go this and go to the right. Right is going to be 0, 1. Going down will be 1, 0. Going left is going to be 0, -1, right? So we have this, and we're going to call it NI, NJ, next IJ equals I plus DI, J plus DJ, right? So we say if Ni, so be 0 smaller equal to Ni smaller to M, and 0 smaller equal to Nj smaller to N, then we can do, so we say if this and grid Ni Nj, grid Ni Nj is larger or equal to current time, so larger or equal to T, then we say temp dot append Ni Nj to explore. But what is the value of to explore? That depends on the I and J, right? So I would rather write just a small function to check I and J. No, it's actually fine. So we can say, so if on the first row, right, we have, oh, these have 3 possibilities. But like if we go here, and one of this has already explored, right? Yeah, so anytime is already explored, we need to also keep check on the points that has already been explored. Already explored. How do we check for already explored? Hold on. Let me think again. So if we go 4 directions one by one, right? Each direction, I go up, and it's not, it's minus equal to 1. No. We have to know how many we can explore. So we have the next one, right? And then it can be explored. And then when the next one comes up, we'll have 4 directions. We need to know that someone has already been explored before. So I don't explore it. I explore the other directions that has not been explored. And we need to also count how many possible that we have done. I have done everything that we don't include that anymore. So let's say we have, every time we've done it, we can actually change grid, right? If we've done it, we change grid. Because we don't compare this value. So if it's in the queue, then we already know. So we can actually say T equals this, Q equals this. Then we can say grid 0, 0, grid 0, 0. Hold on. Let's say this is a permutation of 0 to n times n minus 1. So every value is going to be different. I didn't see that one earlier. Every value is going to be different. So there is no value that's repeating itself. Do we have to change because we know this new information? Well, that just means from one value, then we go to the next. So we hit the next. No, I think it's fine. It just means we have the start and yeah, it means we still have to do the same thing. Okay, I don't think it means anything. So now this means we have visited 0, 0 already at time t, right? So we put this as minus 1, right? And then we check 4 directions, right? We check 4 directions. And if the direction is, if it's good, this is larger or equal to t. Yes, if it's minus 1, then it's not going to be good. So if it's larger or equal to t, now we know this one we can visit, then we try to visit it, right? We put it into the temp. Now, how do we put it into the temp? We need to also know where it is, right? So we say, if you are not visited before, then based on I, so I'm gonna say new to explore, right, equals 3, because we have a one direction already taken from the one that came from. And then we say if ni is 0, the first row, or ni is n minus 1, the last row, then if the first row you cannot go up, if the last row you cannot go down, so your new to explore minus equal 1, right? And then if your nj is equal to 0, the left column, or nj equals n minus 1, or the right, then you cannot go left, right, you cannot go right. So we're going to do new to explore minus equal 1. This means, like for this thing, it only has 2 directions to go. One is here and the other is here. And if you are here, then you only have 1 direction to go because you came from here, so this direction you do not go anymore. And you cannot go up, you cannot go, so you have 1 direction to go. So we do this, right? Then we add it, we add that. Actually, it's going to be, I like it to be all tuple. No reason, no particular reason. I just like it to be tuple, so I'm gonna put a tuple. So this one we'll add to the temp and to explore minus equal 1, right? So we have, this is the parent to explore minus equal 1. So we go through 4 directions, right? And then when I check, we say if to explore, then we say temp.append I, j to explore. Again, that means we have still something to explore, right? Now, after this, we'll go through everything inside the queue, right? Then we're going to check the temp. We say if temp, then q equals temp. Then we go back again. Else, if not temp, then we break, right? Then we break. If not temp, that means at my current level, all right, at my current level, I cannot reach to the next. But that's actually not possible, right? So no, hold on. If temp q equals temp, hold a sec. I think we'll always, like if we don't reach anything, Yeah, so that's the thing. Like we have to go until temp is empty because we want to reach a point where at the current time point there's no more we can go, right? So if we have temp, we q equals temp, and we do it again. We do it again. We do it again until we reach the point where every cell in the queue is the end point. Like they just cannot keep going into any other position. And here also, like if a cell has explored all four directions, all the directions that's possible, then this one doesn't have to be in it. So we don't do it. We are not including the temp as well. And once we cannot do anymore, then we break out, right? Then we can say t plus equal to 1. We go to the next one, and then coming back up. And we will always reach the end because it is possible. It's a permutation. So worst case scenario, we reach the maximum number, then we can reach the end. So this one, we don't have to worry. This one, we worried here. And all we need to do is here, if it's something is reachable, right? I'm going to say if ni equals n minus 1 and nj equals n minus 1. So we already can reach the end. Then we return. Here we return here. Return what? Is the current t? Yes, it is the current t. We return t. Otherwise, we just keep going. And we don't have to worry. We'll always get out. All right? Let's try to see if this one passes. So we have first test case 0, 2, and 1, 3. I believe there's also another one on the outside, right? And output is 3. That's the answer. Second one is slightly more complicated. So copy and paste this one in. And the answer is 16, right? I'm going to hold all of these. Give it a go. All right, so there's going to be grid. Oh, we forgot to do grid minus 1, so we have to do this as well. So how do we do this? Every time we visit? I mean, we can't do that. Every time we visit, we set it to minus 1, and then we say we want to visit the next one. But what if I like to say every time we are going to visit the next one, then we set that to minus 1 because we put it in. That means we have multiple things if they can all reach the same cell, like say this cell, right? We can reach it from here, from here, from here. So if I already reach it, then this one will not go, right? It will not go. Oh, we have complication. We have complication. We have complication. So I just realized that if I set this one, if I go here to here, and I set this one to minus 1 already, then the next one, then we cannot go. Like when I reach here, I know I can go, but now I cannot go. Hold a sec. Hold a sec. It's not you cannot go. It's already been gone, right? So I think the idea is if this can do it. Let me change this a little bit. All right. Let's say this is just a requirement that you can reach that part, right? And then we're gonna say, right, if it's if the value is larger or equal to t, and how is it larger or equal to t? This should be smaller, right? It should be smaller or equal to t. If it's smaller or equal to t, but it's also larger than 0, larger equal to 0, that means it's a thing that you can go. Otherwise, if it is -1, then you cannot go. So I think it should be like if 0 smaller equal to the next one and smaller than t, smaller than t, right? Then we can go. So this is the go, right? This is the go. Right, for this one, 4 directions, and then and if it's this, then we know we can go. And then 2, otherwise new to explore. We have 3 to explore, and then remove all this, and we add it to it. But if the next one has already been seen before, then we don't add it, but we remove to explore. And that one we do not explore anymore. But then we have a trouble because this one will show up every single time. How do we handle that? Let me think. Hold up. Say end here, right? This is the requirement. If this, that means the next one we can go, right? So we say if this is this, and we now have 3. We need to dynamically change the to explore. Change to explore. To explore. I mean, we can choose not to use a queue, use a set. Right? We can choose to use a set. If we use a set, then we can push in exactly the same values. Let's say if the next one we can go, then we add that into it, right? Let's just check around, right? Let's just check around. If all the directions around me I have visited before, then that means I have no more value. So let's not do that. Let's just have this simple, right? So there's nothing to explore. Let's just add more complication. So we just, everything in this will go 4 directions, and we say if it's good, right? If the next one is good, it's within range, and instead we return this. Otherwise, we are going to put this in, right? And that's it. So if it's good, then we put the next one in. We go to the next direction, put it in, put it in, put it in, put it in. And every time we put it in, we are going to say grid 0, 0 is going to be -1. Not going to 0. ij, that means we have visited this one before, right? Equals -1. Now we put nij, right? nij -1. So visited this before, and then we set everything to -1. And then we look at this one, and we're going to look around, right? We're going to look around. And then we're going to set up a flag, right? We're going to set up a flag. And let's say all explored. I'm going to set it to as long as we have, so we need to have um, hold on. I'm looking around me, right? I'm looking around me. I want to know if there's anyone that has not been explored. If yeah, unexplored say equals false, all right? And then for each one jumping in, now we're still gonna do is if 0 smaller than this and smaller than that, right? Then we do this. And Aleph grid ni nj is larger than t. It's actually smaller equal to t, right? If it's larger than t, then unexplored, I think we can have a one word. Unexplored equals true. That means we still have something that's unexplored. It's in a nearby that has a t larger than the current time, so unexplored is true, right? So if that happens, so after we go through all 4 directions, right? Then we're gonna say if unexplored is true, then I'm gonna add ij back because there are something that's unexplored, and these are everything that's been explored, right? So we say it's within a range, and then we're gonna check to see if this one has not been visited before because that's -1, and we can reach it. And then we check if it's the end, then boom, we're done. If not, we set it to -1, say we have explored it, and we put in a temp, right? So next round, if temp, then q equals temp, do it again, right? We do it again. We do it again. And then this one can go through everything, and what happens is we'll have this one, but this is false. So if t is too big, right? False. And then this will be this, and then we'll have unexplored. That will be an infinite loop. We have unexplored, right? With unexplored, we put it in, and coming back up. Hold on. So what we are talking about is if there are unexplored, right? Then we put ij into the temp. So eventually, we need to hit a point where this one is not hit at all, right? So explored is also going to be false. So we're going to have 2 flags. Explored is going to be false. Unexplored can be false. So every time this, we're going to say explored equals true, right? So something is explored. If something explored, now we have to keep going, right? We have to keep going. And keep going, so new temp, a queue, and go. So if nobody has explored, right? Nobody has explored anything, then this one, the explorer will remain false, right? That is actually going to be not here, but on the top level, right? Explored. As long as we have explored something, right? Then so if any explorer, we just put the thing back in, and then go again, right? Go again. We make sure that everything inside the queue. So like if unexplored is false, which means there's no unexplored anymore. how do we identify that? So we come in the 4 directions, right? 4 directions, and um, everything nearby is a -1, right? Is a -1. Then unexplored will not hit. And then if this one's not hit, then unexplored will be false. So if unexplored false, we don't put ij again. And every time we go again, go again, go again. And then once we finish checking everybody, we will always do q equals temp, right? We'll always do q equals temp, but we're gonna check if not explored, right? If nothing, if we have not explored anything, right? If not explored, if we have not explored anything in this round, that means we have reached the end. Now I'm going to break out. We're going to break out current, and then go again. Why do we do that? Why do we do that? I don't think it's necessary. We just, oh, it is necessary. We want to increment t. We want to increment t because we'll only increment t if the current round has no more to explore. Then we increment t. Okay? Say swim in this, gonna pass in grid, run it. They both pass. Okay, let's see. Well, we know it's difficult, so I'm more than happy to check if we have a wrong answer. Oh, this seems to be either a wrong answer. Oh, we got accepted. Oh, we got accepted. Oh my God, I did not expect it. I am very excited. 2 days in a row, 2 difficult questions. I dread to see the runtime though. Oh wow. We're talking about this is the runtime. Holy moly, 100 milliseconds. I am at the end of the end. Jeez, I can't even see. Wow, it got very lenient. Very, very lenient. I can't see. I cannot see. Oh, wow, they got very, very lenient. Look at the actual runtime, the good runtime. We got 40 times slower. But hey, we we did pass this. All right, but might as well consider this as an TLE. All right, so this idea is that we that at each time point, right? At each time point, we find the farthest, right? Farthest cell we can reach from the starting point, right? From the starting point, which is farthest cell in the starting point. We find the farthest cell we can reach from the starting point. But I feel like we probably can improve, but yeah, I'm gonna count this as TLE. I mean, think about it. You're talking about 100 milliseconds is the majority of the answer. You reach 4,000. That is unacceptable, right? That's unacceptable. But anyway, find the farthest cell we can reach from the starting point, and yeah, that is about it. The farthest point we can reach. Every time we go to the farthest point we can reach. Once we hit the end point, we return. That's it. We use a BFS type of searching strategy. For each time point, right, we run the BFS as many times as necessary until all the cells in the queue are at the farthest they can go. Then we increment time and do this again. Runtime is terrible. 4,448 milliseconds. 4048 milliseconds. We pass, but might as well consider this as TLE. Alright, so now give us some kind of breathe room. Let's take a look at a hint, right? Let's take a look at a hint at this point. Use either Dijkstra or binary search for the best time t, which you can reach the end if you only step square at most t. The freaking Dijkstra. I know how to code Dijkstra, but Dijkstra is the shortest distance of binary search for the best time. Well, we can do binary search because everything is a permutation, right? For the best time for which you can reach the end if you only step on squares at most t. How do you do Dijkstra in this? Well, the Dijkstra is for each point, we're going to find all its neighbors. I'm going to keep a priority queue, right? And oh man, Dijkstra. Every time I have to rethink what's Dijkstra. Dijkstra is we have a cost, right? We have a cost, and we want to see what is the minimum cost to reaching the end. So we have a starting point, and then we have the cost of the rest, and each time we're gonna pop out the next node, and each time we're gonna pop out the next node that with the smallest cost. All right, so push this in, and then we pop out the one with the smallest cost, and then from the smallest cost, that one we go to its neighbors, and we update the ones that have already been inside, right? So we update them, and we rerun the priority queue, and then we pick out the ones. Right, how does Dijkstra run? Oh man, this is gonna be like the third or fourth time I try to figure out Dijkstra by myself. I wrote it myself, but I forgot. Each node goes to its neighbors, and then they have the cost, right? And then we go to the one with the smallest cost so far. And then from there, we can go to the next ones as well, and then we can update the cost for the ones, right? So we update the cost. But how do we know which one that we shall go? Oh, it's fine. We just go to the ones because everyone, if I can update you, that means you can reach from me, right? So we update all the costs if the cost to reach you is smaller through me. Yeah, so that's the thing. How'd you update? update the cost, and then how do we update? Cannot update, so it's a priority queue. I mean, you can, I don't know, a dictionary. We need to put an instance, right? I put an instance into it, and it's going to be measured against that value. And then we have what I like a dictionary, so we can update it. After we update it, we can run heapify. So we'll put it on top. Okay, so okay, I see. How do we redo Dijkstra for this thing? The only step on squares. So like we can consider these values. We'll consider these values as the cost, right? So we want to reach the end with a minimum cost. Not the sum, but the minimum cost. So at time 1, say we reach this, so that we reach here, right? So from here I can go the ones we already visited that we don't go again. So we got the ones we haven't gone before. Then we can, for this one we can now go. So wait, so for each cell, when we go to the next one, the one that we can go based on the current time point, right? Based on the current time point, these are the places that I can go. At time 0, this is only at time 1, right? This is the place I can go. And then at time 1, these are the place I can go. Then I choose the one I can go. If I choose go here, what if the time goes high? Then we just wait, right? We wait until we can go. And then we have multiple places that we can go, right? Multiple places we can go. Then we just keep track all of them. Keep track all of them, all the places, right? Keep track all of the places that we can reach from each position. And then we just do a priority queue. Always pop the smallest onto the top. Hold on, I might get into something. So we're starting from the start, right? And we look at all the places we can go, and then we push those into a priority queue, right? And then we go, what's the next step? And then we check the top of the priority queue. If the time is not ready yet, we wait, which is time plus 1. Until time is ready, we pop that one out. And then we push in everything that currently we can reach, right? Because all the nodes that we push into the priority queue are the ones we can reach one way or another. We don't care how we reach there, but we know we can reach there, right? Yeah, we can reach there one way or another. We can reach there. So we just wait until the time is ready. We pop them out, and until we hit a time when the final one is inside. I think that is the one. All right, let's try the Dijkstra. There's no updating. That's different from Dijkstra. I mean, in real Dijkstra, you have to update. You have to update the cost, but there's no updating here. So all we need is have to import heap queue. So we're gonna do a heap. what's going to be inside the heap? Well, the heap going to be it's going to be grid 0, 0, right? That's the first one. That's the heap. And then no. Oh, yes. We have to have a value pop out. And we need a 0, 0. Need a index, right? The index as well. So we say time t is going to be grid 0, 0 as well. That's our starting time. And while true, right? While true, we are going to take a look at the top. So we're going to say if the heap on the top, heap 0, 0, the top is the time, larger equal to t, right? If it's larger equal to t, then we can visit it, so we pop it out. So we're going to say, we don't care, we just care ij equals heap q dot heap pop heap. So we pop it out, right? And then we look at the 4 directions, which we can borrow the code from here. So we pop it out, we look at 4 directions, and we say if it's within our reach, then we just push it into it. But we have to also see, right? We have to also see yes, we push it in, doesn't matter its current time. So we're going to have to do grid 0, 0 equals -1 to indicate that this one has been visited before, right? Equals -1. So so we need to push into the heap without pushing multiple of the same thing to the heap. So it's going to be if this and grid 0, 0 is larger or equal to 0, right? So we don't push in if it has been visited before. So if it has not been visited before, then that's a 0, 0. It's going to be ninj. Then grid, then heap q dot heap push heap. We're going to push. We're going to push grid ninj, right? Grid ninj, ninj. We're going to push this one into it, right? And after we push, I'm going to say grid ninj equals -1, right? This one equal -1. Pop it out and push it in, right? And then we push. If it's visited or it's outside, then we don't do anything. And at the end, right, we're going to say if this, we're going to do this one as well. So if this, then we return, right? We don't have to keep going. We return t. The current t. Hold on. No, we pushed it in, but we don't know when we can reach there. So it's a no. It's not here. It's going to be here, right? It's going to be here because we don't know when it's possible, right? We don't know when it's possible until we reach a t, right? We reach a t. It's like if t is not, then it's not going to be included, right? Even if it's a small value, there's some barriers inside that we just cannot go until we can go, right? It goes t, and large equal to t, and then we take everything, and then I think it should be while, right? While the top is larger than t, then we go through, get everything, then back up. If it's still larger than t, then we go through everything. And every time when we pop, we don't push that one in. So visited, we just pop it out. So it's not, it's while. While it's this. Now we do blah, 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 everything, right? Until a moment came where if I is equal to n minus 1 and j equals n minus 1, then we return the current t. If not, we just keep going until we have the top is not, then t plus equal 1, then we keep going. So solution 2, undefined n. So we forgot to do this. Fail, because we return t equals 0. How? Oh, I think it should be smaller or equal to t. There we go, now it passed. So this is using Dijkstra. Let's see, what's the runtime? Pending. Much faster. Okay, I can feel it much faster. Yep. Ooh, look at that. Immediately. So this is according to the hint using I don't even know how to spell his name. Is it Dijkstra? Like this. Using something similar to Dijkstra. The idea is that for each cell we visit, we push all its neighbors, right? All its neighbors into a priority queue with the grid value being the one to compare. At each time point, we look at the top of the priority queue and visit the one with the smallest grid value, right? With the smallest grid value that is smaller or equal to the current timestamp. We'll look at the top of the priority queue and visit the one with the smallest grid value that is smaller or equal to the time, right? And we push all its neighbors that have not been visited before into a priority queue, with the grid value being the compare, right? With the smallest grid value that is smaller or equal to the current timestamp. Keep doing this, ensuring that each time the cell visited, each time the cell that is visited must be the one with the smallest grid value. The smallest grid value currently reachable. And once the end point pops up, we end the search. We can use Dijkstra because we do not care about the actual path. Every cell we push into the priority queue is guaranteed to be reachable from the start, one way or another. all we care about is that the cell with the minimum grid value gets visited every time. So I guess this one runs at OT. I mean, this one is OT, and this is going to be. Actually, I don't know what this one is. We pop it out, and we go for 4 every time we push in. So I think worst case scenario, every node needs to be visited once, and every node has to also go through. So that's O n squared log n squared, right? It's O n squared log n squared, which actually would run 88 milliseconds. Oh my god, it's even faster. 88 milliseconds. That lands us at a 98% ranking. I'm very lucky with this one. All right, now it's time for us to check the answer and also kind of see what is the deal, right? What is the deal with the binary search? Good. I feel good. I mean, they accepted this, but I think I'm going to be very honest. This is a TLE. Right? No question about it. It's a TLE. I'll just be very lenient that giving me a pass, but I'm not considering this. It's a good question. It's a good question. All right, let's take a look. Modified Dijkstra. Oh, you want me to watch a video? I am not inclined to watch a video. Union find. Oof. Union find. Oh, that's true. I don't have to do that. This is actually just log in. I just realized. Let's just log in. Union find. Okay. First is the union find. Each moment of time, we can update the connected component and wait for the moment when 0 and this are in the same component. Is union find with ranks if we use it with ranks and path compression. Ooh. Oh my god, union find. Using heap, and this is my solution. Alright, union find. Oh, this is what the rank. This one doesn't have path compression. Isn't this path compression? If self, this is the PAR. What's PAR? And a rank. List. If PRX is not equal to X, self.pair X equals self.find. This. I think this is path compression already. Yeah, this is path compression already. PARX. So we're saying that everybody will belong to the same, right? So we turn everything into, okay, that's a smart way. We turn everybody, we can turn a 2D array into a 1D, right? We turn 2D into a 1D. And then when you see from a 0 start, we need to include, right? Everybody can be included in a union. And the find is say if this is not X. Yeah, so that's the root, right? We say if the root is, if the group, right? If the group is myself, then I am the head of the group, then we return. If not, I want to look for my current leader, my current parent. Oh, parent, this is a parent. I look for my parent, and I update myself to the parent value. So this is the compression. Yes. Union. We find the parent of the two. If these two are the same, then return false. That means they're already in the union, so we don't have to do anything. Otherwise, if the rank of this is smaller than the rank of that, remember we have a rank. If this is the case, then we want to union these two. So we know x, y belongs to a union already. So when we union these two, then we say if the rank of x is smaller than the rank of y, then we say parent. I'll give a higher rank. Right? So we give the parent of x equals y. Otherwise, we do this. If they're the same, if the two ranks are the same, then we say y equals x. Two ranks are the same. Y equals to x, or x equal to y, doesn't matter. Then we raise the rank of one of them. We point into x and return true. Why do we return true or false? I don't know. We have union. Yeah, I don't think it's necessary to return true or false. We just like if it's equal, then we just don't have to do anything. Anyway, let's take a look. So we turn everything into a dictionary, all right? In product. Okay. Okay. Then we just say D value equals the it's a reverse. Value equals this. Oh, it's because okay, the value equals the indices, and why did I say DSU? Disjoint union. I think that's what it means. What's the union find, right? And this is this. Grid, everybody gonna be 0. And the nearby neighbor list, okay. So for I in range, it goes for everyone. XY equals DI visited. And for this, if this and grid is equal to 1, hold up, what is this? If the next one we can visit, and the next one it has visited before, right? This one has been visited before. Then we try to union this and this. So this is the current, right? The current one, and this is my next one. Why do we say it has to equal to 1? It just means it has been visited. What is time? Oh, time point. This is a time point. This is a time point. So, okay. Got it. This is a time point, right? So each time point, I point out which one we can visit now. So we can visit this one now. And I look at my neighbors, see if they can all be, yeah, this just means it's available. If it's available, I union these two, right? I union these two. And then I always point things to a, we just need to say if find of these two is nice, very nice, very nice. Ooh. Union find. Good Lord, Union Find. Each moment of time we choose no the smallest value to visit. I reach the answer will be the maximum. I visit cell so far. Is this the keep? Yeah. For this, no, I'm gonna keep how it is in my way. All right. This is how I understand it. This is how I understand it. Push. I had a visited a set. Visited the add. I just set it to -1, right? Then if this is this one, then this is this. Result doesn't matter if you keep. Finally, there is binary search. Ask question, given day D, if we can reach endpoint or not. Alright, this union find is very good. Very good union find. I need to save this somewhere. Let me save this somewhere. I might have saved. Did I save in my gist? Gist. I don't know if I have saved gist. All gists. Alright, so no, there's other people's gist. Well, how does it see my gist? View your gist here. What do I have? Screenshot test. Oh, that's for the article. That's for my article. Dummy button. I think I have a very bad way of organizing my stuff. I think I copy and paste stuff, so I don't really know which one's which. Create binary tree utility function for this. Levenstein. No, I don't think I have. Can I search? Comment one file, two files, one file. This has 3 files. These are all 1 files. How can I don't think I can search. I can search here. I think we have something in the. No, I don't know, man. This is not a easy place. I think I need. You know what? Yeah, don't bother with gist. Gist shall just be used when I write articles. And that's it. What we need is here. Let's do it here. Let's create a new directory we call useful snippet. All right, and then I'm gonna touch useful snippet. Union find. Right, and then I'm gonna copy and paste shamelessly copy and paste this in. and do it our way. DSU, disjoint union. Wait, is that called disjoint union? Disjoint union. Yeah, I think that's what it's called, disjoint union. Is that what it's called? DSU, disjoint union. Disjoint set union. Disjoint set union. Okay, so disjoint set union supports union find in log n time. Right? Log n time supports union and find in log n time. Shamelessly copy from here. So this is parent rank supports time. It has a rank and path compression. But I don't understand this part, which I'm gonna say if they're not the same. If they're the same, right? If they're not the same, then we do this. I don't think I need this. Right? If they're not the same, then I use this. If they're not the same, and we say if this, this, and this, then I'm fine. All right. Thank you for the union find solution. I'm going to shamelessly copy your DSU implementation for my future use. It is shamelessly, right? It is shamelessly. This is a good implementation. I'm actually gonna try this one. Binary search. Who explained binary search? What do you mean? A day D. Wait, what do you mean by binary search? Hold on. If we lay out the entire thing, it's a sorted array, right? So by binary search, we can know, right? Binary search, we know exactly for any day, binary search can lead us to I actually don't know. All right, this one probably binary search. Maximum water levels and all the possible to reach the end. Oh, it accepts O(n) to the fourth. Lowest to maximum water level. No, I don't want to read. Let's go directly to binary search. Lowest valid water level. Search space is sorted and arranged. Binary search can be applied here. Let's take a look. So and size grid, max this, and this are as a left, it's not max, as a left, right, left, yep, makes sense. Now we have mid, visited, while left smaller than right, go to mid, then I want to solve, if solve, if we are able to reach the end with max equals mid, try lower to minimize it. Hold up. So we're going to solve this given the current mid. Which is saying we have the lowest time and the maximum time, right? And we want to see if we can reach the mid with max equals mid. Hold up. So this just saying visited or it's larger than what we're going to turn false. That means with max equal to mid. What's 0, 0? Oh, 0, 0. So we go from 0, 0. But the current water level, this is the water level. So if say the water level is this value, right? Now we try to search to see if we can find it. If we can find it, then true. Otherwise, we set this. We go here. We try it again. If it's true, we can find it. So what we're saying is, if we set mid as our upper level, and we can find it, then we reduce the right to mid minus 1. Then we try it again. Or we just binary search. And this is just a simple thing, 4 directions. It's just a DFS, a simple DFS. A lower. Fail to reach the max, that means we have to go higher. Oh, wow. I see. I have 2 more solutions that we can try. Why does binary search work? If not doing binary search, then we have, like brute force, we have to search. And then that's what he says, right? If we brute force the search, this is a brute force to search. We're gonna go with every single one. Oh, we just solve 0, 0. Lowest valid water level. Let's take a look. This is just a search DFS. Nothing special here. So if DFS current, then we return. Yeah. Otherwise, reset. No visited. Backtrack. We reset everything every single time. So we just add one. So yeah. So we have 1, try to search. 2, try it. 3, try it. 4, try it. Blah 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 blah. And then until DFS we go to all 4. And then we say if we visit something before, then we don't visit again. So that's a DFS. Once we can reach the end, then we return true. But that is going to cause a lot of time. Because every time DFS is going to be O(n) squared. And then we want to do this is O(n) squared. So it's O(n) squared times O(n) squared. But here, the top level is not O(n) squared. The top level is binary search. Right? Because we know if a lower time we cannot reach the end, then it has to be higher. So the top level is O log n, and the low level is O n squared. So it's O n squared log n. Nice. Very nice. All right, 2 more solutions coming. Let's try to see if we can do them fast. We'll go binary search first. I think binary search is easier to implement. There's Dijkstra. I like how the Dijkstra works for me. So binary search, courtesy of I need to. Why did I turn it off, man? I need to copy and paste this thing. So this. All right, so definitely we're gonna say DFS. How would you do DFS? IJ visited, right? Visited. IJ visited. Because we cannot, can we use, then you have to backtrack, right? If you use that, you have to backtrack. No, that's too complicated. I just use visited, right? And then this one's going to give us a Boolean value. All right, this is visited, going to be a set. Yeah, it's too much. I'll just say there's going to be int. It's going to be an int. Visited is going to be a set, right? So what we're going to say is if I equals n minus 1 and j equals n minus 1, then we'll return true, right? What is false? And then we do this. Right, for this, if this, and ni and j not visited, and grid ni and j is smaller or equal to t. Actually, we need to have a max t, current t, right? If it's smaller or equal to t, then we say visited.add ni and j and dfs ni and j visited t. All right. So if this is true, return true. Otherwise, if we go through the entire thing, I return false. That's DFS. And before DFS, we need to specify what is M and what is N. Right? Oh, it's the same thing. Why do you do it twice? You don't have to do it twice. It's the same thing. There's no M. It's just N. Both equals this. There's no M. Everything is N. Yeah, everything is N. So it's the same thing, I. Right? Now we're gonna say left and right. Yes, left equal to max n times m minus 1, right? And then the time, yeah, and then grid 0, 0, and grid n minus 1 and n minus 1. That's correct. So I think we have to put this in this, right? So this is left, right, just n times n minus 1, right? Let's say while left smaller equal to right, and then mid equals L plus right, L at 2. And we say if DFS 0, visited is set, t is mid, it's true, then if it's true, then right equals mid minus 1. If it's false, else, then left equals mid plus 1, right? And we go this right or mid, and then eventually they will equal, and then they will exit. And then we just return L, right? Return L. Will they? No, I don't think they will. Return L. Let's try it. Oh god. I have M. So all the M is gonna be M. And what is this problem? Dict has no attribute. So this is a dictionary. It should be a set. So we passed the first one, but we failed the second one. If it's true, then right equals mid minus 1. It should be what? It should be 16, right? Why would this be wrong? Oh, I don't think this is going to be right. I think it's just going to be max of these two. There we go. But I remember here, I was misled. Oh, it's 2 times n minus 1. Why 2 times n minus 1? Doesn't matter. So that's binary search. So the idea is, right? The idea is given any max time point, we use a very generic DFS to see if we can reach, if we can go from top left to bottom right. Since the time point, since the time point must be a value from 1 to n times n minus 1, we can use binary search to locate the target time point. For a, let's say, say we have a left and right and mid. If we can reach the end, we can find a path. We can find a path with max time point being mid. That means it is possible for us to do better. Then we say we do r equals mid minus 1. Otherwise, we need to erase the time point. So we do left equals mid plus 1. We continue this until the target time point is reached. So runtime is still O(n) squared log n, right? O(n) squared log n. DFS takes O(n) squared, and binary search takes O log n. All right, so this is solution 3. See the runtime. See the giant difference with two solutions. Huh? Runtime is pretty good. Last one, the union find. I'm going to shamelessly plug in the union find. So this is union find courtesy of discuss. Did you upvote this? Let me upvote this. I upvoted this already. So courtesy of this. The idea is to go from to what? To go from time point 1 to n times n minus 1. At each time point, we mark which cell it has become available, and we look at all neighbors or neighboring cells and see which ones can be unioned with the current cell, we do this, right? We after each union, after each time point and the associated union, we check whether the top left and bottom right cells belong to the same union. Very good solution, but we're gonna shamelessly using this. I mean, I will no longer fear union find because I have this. I'm not sure if it's allowed in the interview. It's like, okay, I know this one can use union find, but could I shamelessly plug in the union find I have used in the past? That would be funny. So DSU equals DSU, right? I don't think I need to plug in anything. Oh, n. N is gonna be land grid. Right, so that's gonna be n times n minus 1. That's the total number. Actually, no, it's gonna be n times n. Right, so we need to know. So we need to know the reverse. So we need to say the mapping. Right, so it's gonna be mapping equals this for I in n in range n, j in range n, and then this one is going to be grid I, j, it's going to be ij, right? That's possible because every one occurs only once, right? So this is the mapping. Now we can go for t in range n times n. We're going to say this is the mapping, right? Okay, use grid. So grid, so we're going to say ij equals mapping t, right? And once we do that, we say grid ij, we visited already, equals minus 1. And then we are going to union union these two. So what we're going to do is we're going to say this thing. Where? This thing. All right. For this, we'll have this. If next one is good and has been visited, right? So if grid, this is equal to -1. All right, that means equals -1 is not that it has been visited. Yes, this is a sentinel that this cell is available for union. So if this one next cell is available, then we say DSU dot union. What's going to be I? So we n times I plus j, right? 0, 1, 2, 3. Let's see. If I have this 0, 0, 1, 0, 2. So 0 plus j. Yeah. How about this one? 1, 0. Should be 0, 1, 2, 0, 1, 2, 3. Should be 3. So we can say n is 3. So 3 times I is 1 plus j. Yeah, so that's true. So union this and n times ni plus nj. So we union these two together, right? And then once we go all through, then we say if DSU.find 0 equals DSU.find find n times n minus 1, then we return t. Right, this is solution 4. Pass. Union find is absolutely beautiful. Solution 4, union find. Submit. Yeah, slightly longer because of the overhead of setting up union find, but the code is actually very simple. The top definitely is binary search. I think this is binary search. Dijkstra can work, but binary search is the thing. DSU is just union find. It's such a good algorithm. Gotta memorize this, man. All right, that's it. Oh, we have a good one. We have a good one. But I am going to be very honest. We did read the hint, and without the hint, it's a pass. But I consider that as a TLE. All right, that's it. That's it for today. See you guys tomorrow. Adios.